Okay, I just started the live stream on YouTube. And we start the session now. Hi everyone, welcome back to another exciting sessions of the Data Science Summer School 2025, organized by the Hertie School Data Science Lab with the support of the Hertie School and the Dieter Schwartz Foundations. As many of you have already known, since you've already attended a few of our sessions, the summer school is designed to equip you with both the theoretical foundations and the practical tools that you need in order to tackle complex real-world problems with data. And today's workshop is especially important for anyone looking to deepen their understanding and knowledge of the mathematics that underpins modern data science. So how can you organize large quantity of data efficiently? So as soon as we talk about linear regressions, clusterings, or network analysis, or machine learning or deep learning, we inevitably bump into linear algebra. So it's a language of vectors and matrices, and it forms the backbone of many of the algorithms that I use in data science today. And so this workshop is designed especially for students and professionals and people who may not have taken a formal course in linear algebra before. You'll learn some extensional mathematical concepts that serve as the prerequisites for topics like machine learning and causal inference as part of our Master's Data Science program. And you'll see how linear algebra can be applied in practical ways, and for example, in how to manipulate and transform image data. And so now maybe for a little bit of housekeeping, everyone in the session has your microphone and video turned off, as we have quite a large audience here. You can put your question in the chat or in the Q&A here, and the instructors will try to answer them, or we will remind him when it's needed. And so I think we've had a few sessions before where people raise their hands to speak, but then I think there's some issues with your mic, or because you don't have the right permissions. And so I think for the sessions going forward, we will try to keep all the questions in the chat or in the Q&A box if possible. If you have any other questions afterwards, feel free to email to me or to Christian as well, in case you have any confusions about the sessions that you need clarification on. And so now I'm very pleased to introduce your instructor for today's sessions, Dr. Christian Rother. Christian is a professional Python and data science trainer with over a decade of experience teaching programming and computational thinking to researchers, scientists, or developers across Europe. And he has a background with molecular biology and bioinformatics, and he brings both scientific depth and a hands-on approach to his workshop. I've been in his workshops before for our Masters of Data Science for public policy students, and he's a very fun instructor to have. And so I think you will enjoy the session today. He's also the co-founders of Academist and the author of two well-regarded books, Managing Your Biological Data with Python and Pro-Python Best Practices. And he's known for making complex topics and subjects approachable. And so Christian's specialized in clean code, testing, and practical data flows. And so we're very happy and lucky to have him here today as our instructor. And so with that, please join me in welcoming Dr. Christian Rother.
Yeah, thank you, Hui, for the introduction. I would like to welcome you to this workshop on that. I gave the title, The Geometry of Data, Linear Algebra in Practice. And I was thinking for a moment, maybe the linear algebra in practice should really go on the top, because what I want to do here is to give you an overview of not only what linear algebra is, but also what you can do with it. Yeah, so we will have a mix today of fundamentals and practical applications, because that is where I'm coming from. What you can expect from this. Yeah? So my main goal for today is to introduce you to the fundamentals of linear algebra, that is giving you some understanding, a little bit of language that you can use to continue learning the deeper parts of it on your own, to understand what this whole topic is about. And then, of course, enable you to execute Python code that actually does things with linear algebra. And on the way, I want to combine the two and create some plots and pictures that visualize data in a couple of different ways. So we are going to create a small bit of eye candy on the way, because I find that these are very useful things to that you can hold yourself on during your learning path. I had a very early contact with the topic without actually using it. When I did my PhD, we in my PhD thesis we worked with 3D molecules, so there was a lot of turning around molecular structures on computers. I was aware that there was a lot of linear algebra behind it, but I was able to dodge the topic for a while during the time. It came only much later to me in my freelance career, when I realized that data science is a thing, and that lots of the methods that we've been working with in research are now called data science. And a lot of things that I had been in touch with before popped up, and somehow linear algebra ended up to be a recurring motif. And I would like to dive into the basics of it, because I had the experience in the beginning, when I started to read about linear algebra, that the topic can be a bit scary and oblivious, because there's a lot of math lingo in it, but it's actually not that bad. This workshop comes with a couple of exercises. You find here a link where we have the presentation slides as a PDF, as well as a set of 8 Jupyter notebooks that are also uploaded to Google Colab. So you can open these and execute the exercises as we go along. I will also go through the exercises here during the workshop myself, so that they are present in the recording in case you would like to come back and take a look at the solution. A lot of it is going to use what I call the standard data science stack in Python, that are the libraries NumPy, Pandas, Seaborn, Matplotlib. I think many of you have heard about these or used these already, because I think these were topics in the previous days of the summer school. I have 2 or 3 examples that involve scikit-learn as well. And there's finally the final example is using the spaCy library, which I believe would probably not work on Google Colab, because it involves quite a sizable download. This is why I put that to the end. Now, let's see what we are working with. What is linear algebra? When you look at it from afar, from a 10,000 feet view, it's nothing scary. Yeah, linear algebra is a set of shortcuts for common math operations using larger data sets. Yeah, so that means that mathematicians, they invented a short notation because they did not want to write a lot of things for common arithmetic operations, and they turned to be very useful when working with larger data sets. Linear algebra has a very strong footing in geometry. So everything we do here has a geometrical aspect, as we will see. But the way most people use linear algebra today is actually doing data analysis and powering it to the upper levels, that is machine learning, that is neural networks, artificial intelligence, if you like to use the word. That is all based on linear algebra. And if you want to understand any of these on a more than superficial level, there is no way around knowing some fundamentals of linear algebra. The good news about this is that you don't need that much. Linear algebra goes very deep, yeah, but to get practical knowledge of it that is sufficient to understand machine learning methods, you don't need that much, and we will be able to cover all the fundamentals in this 4-hour workshop, and should still have plenty of time for practical application examples. I put all the topics that we are going to work through in this mind map structure. We are going to start on the top with vectors, and then quickly move to matrices, and see a couple of things that you can do with vectors and matrices, such as calculating distances. We will very soon move to a special type of matrix, and I think this special type of matrix is so important that it was worth a separate point here in this diagram, that is the square matrix. And from there, around those on the left, at the right, and the bottom, you find different types of applications that we are going to cover one by one. And I'm going to start with the vector topic. After the vector topic, we jump to the first exercise notebook. Then we continue with matrices. After the matrices, I think latest there we will have a short break, and between either after item 3 or 4, we will have our halftime break, and in the second half we look at the different applications. I'm going to stop at after every section and see if there are questions in the chat that I can answer. So please feel free to post your questions as we go. I have your chat on my screen visible all the time, so I see what you are writing about. So if you have a question, please do not hesitate to ask it. Short remark: this whole material is available under a Creative Commons license. So in case you feel you need to reuse this, incorporate some of it in your own work, use it for explanation in a thesis, whatever, this is perfectly fine, given that you attribute the original source. This doesn't come with a lot of strings attached. With that, I think we are ready to go. Let's dive into our first topic and see what vectors are about. And I'm going to start with a small definition. I looked this up in a textbook, even though I've known this for years. A vector is a geometrical entity that has a direction and length. Yeah, so you can think of this as an arrow in a coordinate system. Now, most of the arrows that we draw are on 2D coordinate systems. Like if I draw an arrow on a piece of paper, it has a direction and it has a length. The first thing where things start to get a bit more interesting in linear algebra is that arrow can be in a many-dimensional coordinate system. So I can imagine a 2D coordinate system, a 3D coordinate system. With a 4D coordinate system, things get hard. But what people actually do with linear algebra is they use coordinate systems with many thousands of dimensions. The cool thing about linear algebra is that the rules that we learn here with few dimensional coordinate systems, they do not change a lot. Yeah, so it still works the same. Another way to describe a vector is to think of it as a data item, a data point that consists of several different features. Yeah, I say if this were a data analysis workshop, I would say you can think of this as a row from one of your tables. Yeah, like a pandas data frame or something. The only thing where linear algebra differs quite a bit from data analysis that in linear algebra, all your features, they have to be numbers. Yeah, more precisely, they have to be real numbers. Let's have an example. So let's say you go fruit shopping and you want to store the amount of fruit that you have shopped for each type. Let's say we go into a shop and we buy 3 apples, 2 bananas, and 1 cherry or 1 kilogram of cherries. We can put these in a vector, and here I use this to basically show the notation for vectors. So I wrote I called my vector fruit. It has a little arrow on top of it to show that it's actually a vector. This is one way how you can recognize vectors. Now, many people, for example, those who write research papers on machine learning, they do not include the arrow explicitly. Yeah, but what is common for vectors is that you usually have lowercase letters. And then you have the values for the vectors for each of the 3 dimensions, in this case, in brackets. Now, most people use round brackets. Some people use square brackets. There is no difference. It's just it's just a matter of preference. The meaning is the same. And if this is a 3-dimensional vector of fruit, but there could be this column of data could go on further. Now, what can you do with vectors? Yeah, so the first relief, if anyone was a bit scared of the topic until now, is that very, very many operations with vectors, they are actually a disguised form of primary school math. Yeah, like if I want to add 2 vectors, gosh, I messed up the minus sign there in the middle part. If I add 2 vectors, that means I'm going to add 2 elements. Please imagine here in the middle, it should be A plus B and not A1 plus B1 and A2 plus B2, not minus. So we add up the individual elements. Yeah, so the result of the vector addition would be a new vector where we have 7 apples, 7 bananas, 7 cherries. If we interpret the vector addition geometrically, yeah, we get a new vector that is obtained by putting the 2 arrows, one attached to the other. And with the minus, you basically connect the tips of the arrows, and there you have your new vectors. This is not very difficult to do. But then, if we continue on the possible arithmetic operations, we arrive at multiplications, and here things, in fact, do get a bit more complicated because it turns out that there are at least 4 different ways how you could multiply vectors. Yeah, there are more than 4 types to multiply vectors, but I reduced this to the 4 most important ones and left the other ones out because they are very special, and most of the time you would not need them. And my main goal for this first part of the workshop is to walk with you through all the 4 types of multiple vectors, first here in the presentation, and then we switch over to the Jupyter Notebook and see what Python does with this. So the first one is a scalar multiplication, means that we take a number, a single number, and multiply it with the vector. And this is probably the easiest one because this the scalar multiplication means that we take the scalar and multiply it to each item of the vector. We get a new vector that has the same size, that is the same number of dimensions, and geometrically that means it makes your arrow longer if you have if you multiply it with a number bigger than 1. If you take a number between 0 and 1, it makes the vector shorter. And if you multiply a vector with a negative scalar, it changes its direction by 180 degrees. Scalar multiplication is dead easy. The next type of multiplication is the component-wise product. That is, you multiply two vectors, but do an element-wise multiplication. And there is a very handy everyday example that if we take our vector of fruit amounts and we take a second vector that contains prices, then we could use that to calculate the price for every type of food. Yeah, like if if apples cost 2 euros and we buy 3 of them, that means we pay 6 euros for apples. We pay and we pay 2 euros for bananas and 3 euros for cherries. So again, like with the scalar multiplication, the result of the component-wise product is a vector of the same size, but in the scalar product we multiply each part of the vector with the same number. In the component-wise product, we multiply each item with a different number. Yeah, so that is the main difference, that instead of a scalar, we are multiplying here with a vector. The symbol for the component-wise product, I looked this up and I found this slightly bigger dot with some empty space in the middle. This is something that I do not see very often. Yeah, because the component-wise product most often appears in the form of the third one. That is the dot product. And the dot product, this is the main workhorse of linear algebra as it is used in 2025, because the dot product is powering half of machine learning and almost all of neural networks. And the dot product is it's basically answering a very simple question in our fruit example. How much do I have to pay for the fruit when I go to the checkout desk? That is again something that intuitively all of you can calculate. I want to focus here on the notation. Yeah, so when we do a dot product, we denote this by a smaller dot this time. So then we do this component-wise product from the previous slide, and then we sum up all the results. Yeah, so we pay 6 euros for apples, 2 euros for bananas, and 3 euros for cherries. We sum up everything, and then we get a sum of 11 euros. So the dot product takes two vectors and makes a single scalar number out of it. Yeah, so it kind of condenses or summarizes summarizes a vector into a number, and that is a very useful thing. The dot product also has a geometrical aspect. It's a projection, but I found that this is very hard to explain in practice, and it's even harder to draw it because there's a lot of it depends. So I did not find it very practical. I find this fruit shopping example a lot closer to what the dot product does when we actually use it for something. We have a question. So yes, so the sum of all the fruits you pay is the dot product. Good. We have a fourth type of product. That is the cross product. Yeah, that is very important to know that this is a kind of thing that linear algebra is actually good at. It's not something that occurs all the time in my data science practice. Yeah, but it's important that you can do this kind of thing. What it does, what the cross product does, is it calculates an orthogonal vector. So, so if you have a vector, if you have two vectors and you calculate a third, that third vector will be in a 90-degree angle to the two others. And that is something that only makes sense if you have 3 dimensions. It also makes sense if you have more than 3 dimensions, but let's limit this to 3. So so the cross product is indicated by this this cross symbol, and we will get a new vector out of this. And I think that we will see an example in the exercise in a moment. There are 2 remarks that I have to make. One of them is that the cross product is non-commutative. That means if you swap A and B, you will get a different result, and that is a very common theme in linear algebra. You will have to be super careful about the order in which you put your things into math operations. Not only in this one, also later on when we see matrices, because most of the time it matters, and that is, I think, a very important difference between high school math and linear algebra math, because in like high school algebra and primary school algebra, most of the time the order of the arguments does not matter unless you do division. The other thing about the cross product that we should also see in the exercise is that if the 2 vectors A and B are collinear, that means if they are pointing in the same direction, we cannot calculate a cross product. We are going to get a 0 vector out of it. That 0 vector is actually a special vector that deserves to be mentioned. There's not much to say about it. It's a vector that only contains zeros. Another commonly used name for a vector is the unit vector, that has a length of 1. More specifically, one of the numbers in the vector is a 1 and the other numbers are all zeros. And they can be used to define a coordinate system because your unit vectors, they are always going to be aligned with the axis. That's all we need to know about vectors for now. Let's look at our takeaways. So first takeaway is that linear algebra is a set of shortcuts. Then vectors are arrays of numbers that either represent a geometrical entity, like a direction and a length, or they can just represent data. And we have seen that there are 4 different ways to multiply vectors. And let's put these into action. Let's see what we have in the first exercise. Yeah, here is the link again to the page. I think I might be able to put this one in the chat box, just in case you need to type this. And there you find a link to Colab notebooks and to Jupyter notebooks that you can open either locally or in case you have Colab on your own machine. Good. I switched to the exercise. I see there's a question on in the chat box right away. I'll switch to the first exercise notebook here, which is this one. Yeah. So this may look a little bit differently in Colab, but this is how it looks on a local Jupyter server. I'm running, in case you haven't seen Jupyter before, then you can run these with this small triangle button here on top. You can run all the pieces of code. In case I prefer the keyboard shortcut. I use Shift Enter because it's faster, and I don't need my mouse. I only need one hand for it. So Shift Enter executes these blocks of code. In case you get a module not found error, yeah, then that means that, for instance, if you see no module named NumPy, that means that NumPy is not installed. Most likely this is happening in on a local machine if you have a fresh Python installation and you haven't worked with pandas in the other workshop parts. You can try this. Make a new empty cell and try Python -mpip install NumPy and execute this, and do the same for the others. We could add these here: lib, seaborn. So so the exercise link is here. Okay, I'm catching up with people in the chat box, trying to find the exercise. I could see if I can copy the link directly into the chat box. Maybe that helps you. I'll wait a small moment before we move on and see if there's further questions on this. I think the Colab notebooks, they should come with all the important libraries pre-installed, which is what makes this Python stack that we are using here very beginner friendly, in my opinion. Okay, I'm getting positive confirmations from some people that apparently this worked. Let's see what we are doing. I put here at the beginning a piece of eye candy. So just that you see, okay, you can actually create nice things with linear algebra. Yeah. So what are we doing here? Yeah. So we are creating a vector that contains 1,000 numbers. The first number is a 0, and the last number is a 30. And all the other numbers, they are evenly spaced in between, and we are using that for the x-axis. And then we are using matplotlib to create 10 sine waves. So and the sine waves, they are created with this np.sine function. And what that is doing is it takes our vector of 1000 numbers. We might want to take a look at this vector, at least at the beginning. Here, this is how a vector looks like in NumPy. These are the first 10 of 1000 numbers, so they are increasing slowly. And this sine function takes each of them and takes a sine. Now we are adding a scalar to each of them to basically shift the phase of the sine wave. So we are moving the sine wave a little bit to the right. Matplotlib automatically creates the colors if you make multiple plots. So the nice thing about this, that if you want to do something like a sine function on a vector, NumPy gives you that type of functionality out of the box, so you don't need to write an extra loop. Yeah, one of the great benefits of NumPy is that it makes loops go out of the way. Let's see if we can create vectors for our fruit example. So regarding the notation here, the name for a vector in NumPy is an array. I think that's because there's an underlying C data structure that is also called an array. And then you put your data items there. I think by default, if I add an A, but by default, NumPy takes the data type that it gets. So in this case, it's an integer. As soon as one of the numbers is a floating point number, the entire vector becomes floating point numbers. NumPy knows different types of floating point numbers if you want to tweak the precision of the decimal places. That is quite an important issue later, but I left that out of this workshop because I don't want to get lost in the technical details. We can create a second vector for another shopping session. So we basically have to fill in a gap here. We write np.array to create an array. Then we need a round bracket for actually creating the calling the array function. And then we need a square bracket to say, now comes the data that is in the vector. And let's buy, I don't know, 20 apples, 10 bananas, and 5 more cherries. And then we have to close the brackets in the opposite order, of course. And now we have two vectors that we can work with. The addition is super easy. It looks like a normal addition, but what we are doing is we are actually adding every position of the vector. The 3 goes together with the 20, and so on. Now the scalar multiplication, in case you wanted to see that again. We can take a scalar, multiply it with a vector, and then every position of the vector should increase by that factor. So before we had 23 apples in our fruit vector, now we have 230. In Jupyter, if I do that operation again, here I'm writing back the value into the same variable. If I do this again, I'm basically adding another 0 to my vector. And we can make a useful data visualization out of a vector. I think the first obvious one is what? Is the oh, I think I missed here. Why this worked before? Strange. I think this has to be written with an x coordinate, or we could actually make this a bit nicer and label our bars apple, banana, cherry. And we get a bar plot from the vector as a very straightforward data visualization. This is the part where pandas becomes really useful if you want to do these kind of things on a regular basis. Pandas adds a nice luxury interface on top of NumPy. Yeah, so NumPy is a useful tool for analyzing data, but pandas makes your life really easy. Yeah, so because it carries on the labels for you and sends them to Matplotlib immediately. I think that is what I missed out here in the example in the first place. I think we have a few more types of multiplication to cover. For instance, we have the position-wise multiplication, and here our fruit prices come in. That is a price for the apple, a price for the banana, and a price for the I don't know, that must be a single cherry. And now we can use the multiplication operator to multiply our fruit vector with the prices. And the result of the position-wise multiplication is, again, a vector. I think we had 2,300 apples in the fruit vector before. Now we have 2,300 euros. The bananas are cheaper. This is why I think we had 1,100 bananas before, and similar for the cherries. So this position-wise multiplication is the one that in the math notation is the one with the small circle with a little gap in between. Now in the dot product, we sum up this whole thing. And we will see this NP dot operation a couple times more here. Yeah, so we put in, but you need to remember about the dot product for now is that it needs two vectors again. So we put in the fruit, we put in the prices, and what we get back is a single number that is the sum of everything from the position-wise multiplication. Good. Final one, the cross product. Easy example. Let's say now the fruit example does not make any sense if you want to create cross product, because the cross product makes you vectors in a 90-degree angle, and we need three-dimensional vectors. So I'll take an example, x, y, z directions here. So my first vector is an arrow pointing along the x-axis. My second vector is pointing along the y-axis, and the z value is empty. Now, when I want something that is orthogonal in a 90-degree angle to the x-axis and in a 90-degree angle to the y-axis, the only choice that I have is that it's going to be a vector along the z-axis. And that is what the cross product does. Even if your vectors are not perfectly aligned with the axis, you will always get something that is in a 90-degree angle. The mathematicians sometimes call this a normal vector. Good. Now, there's a couple of of things that you can that you can play around with. That is most importantly is there's something happening when you have these orthogonal vectors that has to do with the dot product. Yeah, let's say we save this cross product vector in a variable c, and if we want to do a dot product of two vectors that are by definition orthogonal, because A and C, they now should have a 90-degree angle. They really have nothing in common, and the dot product is zero. Yeah, so this is something that you would expect every time you use orthogonal angles. Now here there are a couple of exercises that you can that you can try yourself. So here are a few vectors, and you can see if you can use the dot product to find out which of them are orthogonal, or you could use the cross product to find out if they are collinear. For instance, if I want to calculate a cross product with two angles that are pointing in the same direction, that means they have to be collinear, then I cannot calculate a cross product. I need really to have vectors that point in different directions. Otherwise, I will get a zero vector. And the same would happen if we put in two orthogonal vectors. Like, these are the border cases that one has to be aware when multiplying vectors. I placed here at the bottom a couple of things that I consider useful when doing this kind of stuff with NumPy. This is mostly self-explanatory, with the exception of the parabola, and I will fill in the gaps so that you have a solution to take away. So this linspace function creates as a numerical vectors. Let's say I want to have numbers from -10 to +10, and let's make 1,000 of them. And a parabola is I want to do a square function. So I could use a square function by calculating x times x. That will do an element-wise multiplication. In NumPy, I'm also allowed to use the power operator that Python has, and that should have the same effect. So every number in y will be the number in x to the square. And when we plot this, we will get to see a nice parabola. So we see that these vectors, they give us a really compact way to handle, like, not only their own vector operations, but we can also use them to calculate like common mathematical functions. Good. I'm checking the chat box at this point if there are any questions. I think this is a good moment to take like a 5-minute breathing break before we move into the topic of matrices. So if you need some air, if you need some water, then please take your time. I'm setting a timer here, and we will continue at precisely 9:53. Thank you, and see you in a moment. When I come back, the first thing that I will do is check the chat box for questions. Thank you.
Hi, Christian. I'm sorry.
Yes.
This is Aliyah here. I'm helping Hui with the session. I just wanted to let you know that there were two questions in Q&A section. So maybe you can look at them later after the break, after the little break.
In the Q&A section, can you
Yes, so there are two questions. The first one is, this might be a very basic questions, but why are we using vectors to do calculations in the first place? How does it help in data science aspects? Just trying to understand, is it to make easy calculations or things which have different
I
aspects?
see.
Yeah. And the second
Okay.
question, yeah, or
Okay, I found the Q&A window. Thank you. I wasn't aware that there's a separate one. I'll put this on my screen and I'll answer these. Thank you, Alina, for pointing out.
yeah, you're welcome. Thank you.
See you in a moment. It's 9:53 on my clock. Let's continue. Thanks, Alia, for pointing out that we have a separate Q&A box. I found two interesting questions there that I would like to answer right away. The first one, I take the shorter one first. What does it mean if two vectors are collinear? They are parallel. Yes, that is correct. Collinear and parallel is more or less the same thing. Collinear is used for vectors because the vector also has the direction aspect. Yeah, so if two vectors are collinear, that means they are pointing in the same direction, or I'm not entirely sure. I would have to look up the precise definition. I think they could also they could also point in exactly the opposite direction. Yeah, so the parallel is used mostly for straight lines that are infinite, so they don't have a length and they don't have a direction that they are pointing to. Yeah, I think this is why collinear is used in the vector world. Then we had a fundamental question: why are we using vectors in the first place, and how does it help with data science? Yeah, so one way to think about this is you can think of a vector as a column from a table with data. Yeah, like you can take any data that you have. Like, I don't know, let's take if you have a table with all the countries in the world, and you have a column for the population, you can take the population and call this a vector. And or if you have a table with employees and a column that has the salary of each employee, you can make that a vector. So it's basically a tool that we can use to take, to stick with the country example, to take all the country information on the population at the same time and represent it by one mathematical symbol. Yeah, because I will want to do something for all the country population numbers anyway, to, let's say, I don't know, calculate a projection of how the population is going to develop. Then it's going to help us that we can refer to all the data items by one symbol. I think that is why people are using vectors. I hope that answers the questions. So then we have a question: is there a quick way to add numeric labels or values to the chart? That is so with a bar chart with Matplotlib, I found that this is not quick. I think if you want to label the bars with the respective numbers, then I might want to look at the Plotly library. At least this is not something that we can do very quickly. If you are interested in making quality plots, then I strongly recommend to go to the Matplotlib gallery or the Seaborn gallery, because there you find lots of Python examples for different plots that you can copy paste and then modify. So if you want to do like slightly more sophisticated things, this is a good starting point. But let's continue with our second topic of the day, which is, I think, very central to the entire field, and that is matrices. Yeah, and I found matrices a bit scary when I first heard about them, and they remained scary for a while, but actually they are not that scary if you look at it a bit closer. But there's a few things that I still find a bit confusing. Let's take a look what we find here. What is a matrix? For many practical aspects, you can think of a matrix like a table with numbers. So it's when a vector is a single column, then a matrix is multiple columns. If I want to define this a bit more formally, then we can say a matrix is a two-dimensional array with real numbers. So instead of one person going shopping, we now have two persons that go shopping, and they both buy apples and bananas and cherries. Only that the second person does not like bananas, so there is a 0 in the banana position here. Yeah. So so every column here would be a different person, and the rows are the different types of fruit. And I won't cover here the addition and scalar multiplication with matrices, because they are very they work in exactly the same way as with vectors. Like if I add to matrices and they have the same size, then I can add the corresponding positions, and if I multiply everything by 10, then I do a scalar multiplication of the entire matrix, and I would have to add a 0 to every number that we have here. What we need to know is that matrices, they are usually written by capital letters. Yeah, and this is a very strong mathematical convention. So if you see a paper or a blog post that does something with machine learning and you see a capital letter, then it's usually a matrix. If it's not, then it's probably explained in the text. But this convention that capital letters are matrices is so strong in the data science field that people don't explain it when they write about it. The second thing is that matrices, they have a dimension that is the number of rows and the number of columns, and the number of rows comes first. And that is something that you will have to keep in mind, because this is, when you start doing data science stuff yourself, this is one of the main sources of bugs. So the rows come first. Because there is this source of bugs that is related to the dimensions, I put here in the spacer slide that we need to have a way to analyze how big a matrix is. So if you create a matrix in NumPy, here's an example. First of all, we have 2 pairs of square brackets. We are also using the array function, but it has 2 square brackets, one for the rows and the other one, the inner one, is for the columns. And this d.shape operation tells you how many rows and columns your matrix has in exactly that order. Yeah. And I recommend you to put this .shape in your pillow when you do your first steps on NumPy and when you do your first steps on pandas, because on pandas .shape also does work. And if you do more advanced stuff, you will still use .shape on everything, because when I was learning this, 50% of my bugs were shape related. Yeah, so you need this all the time to find out, is the number of rows and columns the one that I am expecting, or did I accidentally swap them, or did I make some other mistake somewhere else? As this is when you do linear algebra using a computer with Python, .shape is your most important debugging tool. There is a operation called transpose. That is the first matrix-specific thing that we can do that was not really that well possible with vectors. That I'm tempted to say it turns the matrix by 90 degrees. It's not entirely correct, because it swaps the axes. So the rows become columns and the columns, they become rows. The order does not change. So what was the first column now is the first row. The numbers are the same. Yeah, now in this transposed matrix, every row is a person that does shopping and every column is a type of fruit. We will be able to do the same thing with vectors, and this is where NumPy works a little bit differently than math notation. This is why I will elaborate on that when we get to the practical part. So now the difficult part, the only thing that we need to know about matrices in this section is how you can multiply matrices. And there's two things that you can do. The easier one is you can multiply a matrix with a vector. Yeah, so you usually would calculate the something like the dot product. So that is, we want to find out if we have two persons in our matrix, we want to find out how much each of the persons pay. So we take our price vector that has the price for apples, bananas, cherries, and we have the amount of apples, bananas, cherries for each of the person. And we can find out by multiplying each price with the corresponding fruit how much they pay. Now, when you see the math notation for this, is then you notice that I transposed the matrix before. Yeah, that has to do with getting the number of rows and columns into the right format. Because this type of multiplication only works in one particular arrangement. That is here. What I found most helpful to understand this is that you need to multiply a 2-3 matrix with a 3-1 vector. You could call this vector a column vector, so that the numbers here in the middle are the same. Only then can you multiply a matrix and a vector. If that tells you that matrix multiplication is non-commutative, like if we swap the prices and the matrix, then it does not work anymore, because the shapes do not match. We need to have this number 3 in the middle of the sizes. There are a few alternatives to this, and I will just show you one of them here. So we could do the same thing the other way around. So we could say, let's put the prices here and transpose the price factor. So that before the price vector was like a column, every price on top of the other. Now they are horizontally aligned. You could call this a row vector that has the dimension 1 and 3. So again, the 3 is on the right side here, pointing to the 3 of the matrix opposite to it. And now we can use the original matrix that is not transposed. The result is going to be the same, only that now the alignment of the result vector is different. Now, and this is hard. If you are confused at this point, then you are rightfully so. Yeah, it took me quite a while to get behind this. Yeah, because the confusing thing about this is the math itself is not complicated. We are doing basic additions and multiplications. This should be easy. Also, the intuitive understanding is easy. Yeah, we know how many fruit everybody of the two persons has bought. We know the prices. We can calculate the numbers. Yeah, so why is this so complicated? Yeah, because the matrices, when you work with real world data, they get much bigger. Yeah, so we need to have some formal notation that is as short as this, because your matrices, they might contain thousands or millions of numbers. So what has helped me to understand this, that is how you multiply matrices generally manually on paper. I'll put up that notation first. Let's say we have two matrices, A and B. and we want to multiply them like here. We calculate the product AB. That is usually written without any extra mathematical signs. I'm multiplying two matrices here, even though one of the matrices could be a vector. Yeah, like if I replace A by a column vector, I have just one column instead of two. And if I replace B by a row vector, I have a row with two columns instead of two rows. The basic rules, they do not change. So how this works is I put one of my matrices that I multiply on the left and the other one I put on top. And then I can immediately see that what is the size of my result. Yeah, so I have two columns in B. I know that my result must have two columns. And if A has 3 rows, I know that my result must have 3 rows. So the result of multiplying a matrix with 3 rows and 2 columns with another matrix that has 2 rows and 2 columns must be a 3-2 matrix. That is the first thing that I can realize from this. Now I can calculate the content of each cell, and that is a normal dot product. Yeah, so I take this vector on the left, this first row of A, and the first column of B, and I calculate a dot product of these. That only works if they have the same size. That is this thing about the dimensions that have to be aligned. Yeah, so the number of rows in B and the number of columns in A, they must be the same. Otherwise, you cannot do matrix multiplication. I think that is the most fundamental thing that you will need to remember about matrix multiplication. It's all about the shape. So now let's calculate the dot product here for this example. I take the two green numbers. 1 times 1 is 1. 7 times 2, the blue numbers are 14. I added them up because that is how the dot product works. I get a 15. Here in the second cell, I multiply the 1 from A with the 3 from B. I have a 3. Then I multiply the 7 from A with the 4 from B. 7 times 4 is 28, plus 3 is 31. And you can repeat the process for all the other cells. And I had to do this a couple of times on the whiteboard or on a piece of paper to really get behind this. Yeah. Matrix multiplication brings a bit of complexity in the notation because we have two matrices with two dimensions each. The arithmetics is simple, but knowing what to multiply and add with what can be a bit tricky at the beginning. I found a compact way of writing this. So what you need to know is that the inner dimensions are the same, and then you can do a dot product here for every corresponding position. There are some rules in matrix multiplication that is, again, it's non-commutative. AB and BA is not the same. The associative rule and the distributive rule, they work as you are used from normal multiplication. So if you have a bracket, you can move the bracket around, or you can get rid of the bracket entirely. So this is quite pleasant. That means that you can do like almost normal algebra with matrices. So if you feel like like reading a proof of any of the methods that is being used here, you're free to do so. Good. That's in a nutshell, matrix multiplication is doing a lot of dot products across rows of one matrix and columns of the other matrix. There is a special case of matrices, and that is when your two dimensions are the same. And this is where things get nasty for the beginning data science practitioner. Why? Because if the two dimensions are the same, you can swap them and without causing an error. And that is something that is going to happen. Yeah, so this is why I give square matrices a bit of special attention, because they are practically a bit more dangerous to use. They have a hidden source of error, but they also have a couple of nice properties that we can use. So I basically took this here to attach a warning sticker to the square matrix. Okay, so what have we seen so far? So matrices, they are tables of numbers with a number of rows and a number of columns. And you can multiply vectors and matrices. It's a bit similar to a dot product. Yeah, it's not called a dot product, it's called a matrix multiplication, but the mechanics are a bit related. I'd like to stop at this point and see if there's any questions. I have a question here. Can I give a real life example for the need to transpose a matrix? So it's this operation. So I need to think. I need to think for a moment. So I use the transpose operation all the time. It's very central to the type of work that I do with data. Like, let's say you have a table with numbers. Yeah, let's stick to the country example. You have populations, and every row is a country, and every column is a different year. So your columns that you then usually will use as vectors for something, they would be the population of all the countries during a year. Now, if you want to trace the history of the population of a country over the course of some years, and grab that column, then you would transpose the matrix first. Yeah, so the first thing where I find transposing really useful is it's not no fancy math that I need to do. I need the transpose when I want to plot data. Yeah, so when you use the pandas library for data analysis in Python, pandas treats the columns of a table as the more important dimension. So like when you let's say you make a line plot, line plots are made from columns. Yeah. So I need to control what is in the columns of my table. And the transpose is one way of getting the data where I want it to be. Yeah, so you can think that the transpose is not doing anything dangerous in the first place. It's a tool to get the data, to move the data around. I think that is how I would see it. Okay. I think at this point, I see, do we have anything in the chat box? No, at this point, we can see what we have in the second Colab notebook. I think it's the one called matrices. I'll fire this up. I place the imports here again. Yeah, so now I'm the one that is new here is the Seaborn library, which is like a nicer plotting library for Python that is working on top of Matplotlib. And again, I have a small eye candy example here. So when you run this, then this is actually an example of the transpose, and it's a nice example, and I'd like to unravel this for you, because I think this really helps you to understand some of the basic mechanics here behind vectors. Yeah. Let's look at this. The pattern, by the way, it's partially random. Yeah, this is why it's going to look a bit differently for each of you. If I look at this random vector that I generate here, I see that this is a matrix. I recognize that it's a matrix because in NumPy, I always have the word array on something. Then I have a round bracket. This is what NumPy gives me for free. But then I have two pairs of square brackets. Yeah, that moment I know I have a 2D matrix in front of me. Yeah, so when you read output of NumPy code, the very first thing that you have to do, even before checking the shape, is count the number of opening square brackets at the beginning. So I can check the shape of this. And I can read this as a matrix with 1 row and 16 columns. Or you could also call this a row vector. Now we do the transpose. That takes the same data, but it looks quite a bit different. Yeah, we count the square brackets again. We still see it's a matrix. Yeah, but the orientation is different. Yeah, now, and it becomes apparent. I might write, instead of this capital T, this is a short form for the transpose. Yeah, it has the same result. If I inspect the shape of it, I see that this is a matrix with 16 rows and 1 column, or we could also call this a column vector. Good. Now, what happens when I put a row vector and a column vector together? Yeah, so I would have a, let's make this more explicit. In the this matrix multiplication image that I had here in the in my little helper slide here, I would have a very slim vertical vector on the left and a horizontal vector on the top. Yeah, and from that I would immediately see that we get a 16 by 16 matrix as a result. And when we go here to NumPy and inspect the shape of this this matrix that results from this multiplication, then we get to see, we get a 16 by 16 matrix. And this plt.im_show is what takes a matrix and makes an image out of it. That's it. So this is maybe the most straightforward way type of matrix multiplication, because I basically take a row vector and a column vector, multiply them together, and I get a square matrix. Let's look at if we can do the same thing for our fruit example. So here we create a matrix with food, with a shopping list for 2 persons. Yeah, so we have here person 1, and in the second row we have person 2. And the 3 columns, they are again the 3 fruit types. And now when you do this, especially if you haven't done this a lot of times before in your life, you can, the moment you define a matrix, you can immediately follow this up with an m.shape, yeah, because maybe you forget this outer pair of square brackets or one of the inner pairs, and something changes, then you might want to check, is this the number, is 2 rows and 3 columns, is this what I want? Good. What can we do with the matrix? Yeah, we can add 10 to everything. We can multiply everything by 5. Note that I'm not storing these back in my matrix. Yeah, we just I just have these operations here as an example. I'm not going to calculate with these 50 and 20 apples further. We can, of course, transpose the matrix. Yeah, so then this now we have the first row containing the apples. And of that, we can again take the shape. When you work with matrices, this until here, it's like basic bread and butter business. This is not complicated. The complicated part starts when we start multiplying matrices with stuff. Yeah? And to multiply them, I prepared here again a vector with prices. Yeah, and I put in 4 different matrix multiplications, or you can use the dot product function for that as well. That also does the matrix multiplication. Now, some of these will work and some others will not work. And I want you to try out and follow up why some of them are not working. Let's look at the first one. This one works. We calculate the fruit types and the prices, we put them together, we get the result. Aha, person A pays 11 euros, person B pays 8 euros. It's all fine. When I try the same operation the other way around, then it does not work. Yeah, so the dot product or the matrix multiplication is not commutative. You cannot simply swap the arguments of the dot product. Now, why does this not work? The answer is you need the shape operation to check what is going on. Let's check prices.shape and m.shape. When I debug something like this, I would always put the shapes, check the shapes in the order in which I put them into the dot product. So what we have here is we try to multiply a vector of size 3 with a 2, 3 matrix. Now we said before, you can only multiply matrices if they have a matching dimension in the middle of each other. Yeah, so that was the case in the first example, but not in this one. Yeah, so the three from the prices and the 2 from the matrix, they are not matching. This is why we are getting this error. Shapes are not aligned. If we do the same thing, but the other way around, but transpose the matrix, we get the same issue, but on the other side. Now the 2 is on the left and the 3 is on the right, and it doesn't work. However, if we put the prices on the left and the transposed matrix on the right, we get a nice vector output because we have a price vector of size 3 and multiply it with the transposed matrix that is a 3 by 2 matrix. We get the correct result. This is in a nutshell. This type summarizes like how I debugged like the majority of my shape bugs in NumPy and related tools. It's most of the time it comes back to some dot product like operation that is not working because the shapes are not mismatching. Good. What else can we do? I think here's another way of creating row and column vectors. This reshape operation is quite central. It basically says take whatever data you have here and make a 100 by 1 matrix out of it, or you could also make a 1 by 100 matrix out of it. As long as your amount of numbers stays the same, you can reshape vectors into matrices and back if you feel like it. So we could make, if we take a range of 100 numbers and do the same thing as above, we can make another picture like this. And this is created from a 100 by 100 matrix. I can recommend that you explore the numbers in the matrix a little bit. So if we take a look at this matrix D, we see that it starts with zeros in the top left, because here we are multiplying, and it ends with 9,800 in the bottom right corner. And this IMShow function takes these and interprets them as color intensities here in this plot. I have at the bottom a couple of useful phrases. How to make this first one makes a matrix and reshapes it. I think that occurred before. I think this is a more compact version of what we had before. Sometimes you may want to create random matrices, for instance, with integer numbers, and this IMShow takes such a matrix and makes an image out of it. Yeah, so here the resolution is lower. This is why we get this checkerboard image. Before, this is smooth because it's a 100 by 100 matrix. And if you want, you can use Seaborn to make a heat map where you actually have the values written into the heat map. I think this is going to become useful in chapter number 4. Good. I think we are done with the basic matrix chapter. We are going to see more matrices soon, but what you should take away from this is that you can multiply matrices if they have one dimension that is aligned. Yeah, sometimes you need to transpose your matrices to make the multiplication possible. And the transpose operations may help you to get the data into the right alignment. And you need the shape command to check if the number of dimensions is the one that you expect it to be. Good. Now I pause for a moment, see if we have any questions here in the box before we move on to chapter 3. Here is one. How do we check for certain properties of a given matrix? For instance, if we need to check if matrix A is orthogonal, dependent, independent, existent of inverse, symmetric, linear. Awesome. This is an awesome question. We will see some of these in the next section. Yeah, because you're hinting that matrices that they have more interesting properties than the shape. So and I think we are going to see at least two more of these properties. So thank you for the question, but I keep this open because I think the next chapter and the chapters 3 and 4 they should give you at least a partial answer to this. Thank you for the question. Let's move on. We have 25 minutes until the halftime break, so I think this should allow us to take a look at linear transformations. This is chapter 3. This chapter, linear transformations, is theory-wise it is short, yeah, because linear transformations is what you can actually do with matrices, or what matrices are. Yeah, I gave you a geometrical interpretation of what a vector is. Yeah, we started by saying a vector is something, a geometrical entity that has a direction and a length, or more sloppily described, a vector is an arrow. I did not give you anything like that for a matrix, yeah, because because it's a bit more tricky. So I wanted to dedicate an entire chapter for it. The geometric interpretation of a matrix is it translates one vector into a new vector. So it changes a vector into a new coordinate system. You called it a linear transformations. So more generally, I can say that all matrices, they are basically tools that apply linear transformations of coordinate systems. Yeah. So, and we are going to see some examples. So if I multiply a vector with a matrix, I transform that vector into a new vector. Most of the time when you do that, or many times at least, you want to have the number of dimensions to stay the same. Yeah, in that case, you will need a square matrix, and that has a couple of a lot of practical applications. Like everything that has to do with 3D graphics is full of linear transformations. Yeah, like if I do if I have a vector graphics program like Inkscape or Canva, or where I move things around on the screen and rotate them. that is when linear transformations are being done. Yeah, like here in this small picture that I created. And when I do computer-aided design, I do the same thing in 3D. If I have 3D games, like something like the Unreal Engine does, they do lots of linear transformations. And that is historically a very fortunate coincidence. Yeah, because when 3D games started to become popular and people wanted fast 3D graphics, companies like NVIDIA, they started building chips that could do lots of matrix multiplications. And it turned out that the same chips are very useful to use dot products for other things as well. Like, for instance, to train neural networks, because it's linear transformations all over the place there as well, only not applied on geometry, but on something else. And in my own field of research that I worked in 20 years ago, we were rotating 3D molecules there. Also were lots of linear transformations being applied. So here in the picture, we have this image of a house. You can think of the house as every corner being one of the vectors. And when we rotate the house, we basically want to apply the same rotation to every vector. Yeah, so how can we, let's say I want to rotate this house by all my vectors that describe the position of the house by 45 degrees. How can we do this? The answer is we have to find a matrix that represents this rotation. And that is what linear transformations is about. We want to do rotations and a couple of other things. How does it work? There's a matrix with easy numbers, fortunately. Yeah, so this is a simple rotation matrix that rotates vectors by 90 degrees. So we say, so you can think, if you have a vector with 2 dimensions that contain an x and a y position, like here, this 3, 1 vector, this would be my my coordinate that I want to rotate. And I multiply the x position with 1, and it becomes the, no, sorry, with -1. No, sorry, I multiply the x position with a 0, and it goes away, but I multiply the y position with a 1, and it becomes a 1. The 3 ends up in the y position with a minus, because we have a minus here in the bottom left of this rotation matrix. The cool thing is that this will work for every xy coordinate vector, and they will all get rotated in the same way. So if I take this 1 minus 3 and put it back here, I should get a and do the rotation again, I should get a -3 -1, and after 4 rotations, I should end up with the original vector. And this is all described by the single matrix of 4 numbers. So we have a question, is the matrix being rotated or the vector? No, the vector is rotated. So I say here, I take my rotation matrix, multiply it with a vector, and my rotation matrix, I only need this once. This handles all 90-degree rotations in, I think it's clockwise. Is it clockwise or counterclockwise? Doesn't matter. Yeah. So the matrix stays the same. The vector is changing. Yeah, so I basically, if I do this, if I have vectors for all the corners of my house image, then I can rotate them all using the same matrix. I only need one matrix to rotate all my data points. You can generalize this. Yeah, there we get a little bit of more advanced math, namely trigonometry. Yeah, if you want to rotate by other angles. So if you have a 90-degree angle, the cosine, so we have an angle theta. This is the Greek letter theta. Um, and a cosine of a 90-degree angle would be 0. And the sine of 90 degrees would be 1. And the negative of this of the 1 is -1, of course. So for 90 degrees, you get the same matrix that we saw previously. But for all other angles, this also works quite nicely. Now, we can apply the same idea even a bit further. Let's say if we are not if 2 dimensions are not sufficient, then we could say we make rotations in a 3D coordinate system. Yeah, where let's say we want to rotate by the x-axis. So we say for x there is a 1. So that means whatever I do during my rotation, the x coordinate does not change because I'm rotating around it. But the others, the y and z coordinate, they would change. And likewise, I could construct similar rotation matrices for the y and the z axis. So this type of matrix is what powers most of 3D rotation in like CAD and CAD programs and similar. Yeah. Now, the same idea with rotation, you could also theoretically rotate a higher dimensional space if your vector is longer. If you have a vector with 100 numbers, you could still rotate it using a matrix multiplication. Yeah, note that when you do this, your matrices, of course, they get bigger because your matrices that do this type of rotation, they have to be square matrices. There are other linear transformations. Yeah, like let's say we could make the building twice as big, so we can scale. We could only scale in one dimension, so stretch it in the x dimension. Or we could do some stranger operation that we kink the whole coordinate system a bit to the right. This is called a share operation. Yeah, so they have, these are all examples of other linear transformations. We could also swap the x and y coordinate around, and it would still be a linear transformation. They have in common that the angles between the axes, they might change, but generally the proportions between your points, the distances between the points, they are mostly maintained if they are along an axis. So mechanically, this is still using matrix multiplication. Yeah, but your matrices, they may look a bit more complicated. Good. Now, there is a special matrix that we come across when we examine these matrices that do these linear transformations. That is the identity matrix that has a special function. The identity matrix in the first place looks very boring. Yeah, because it's full of, the identity matrix is full of zeros. all it has is a diagonal full of ones. Yeah, that means that if you multiply a vector with an identity matrix, it does not change at all. This is why it's called an identity matrix. So identity times some vector is resulting in the same vector. And also, just because we did not mention this before, there's also a null matrix, that is a matrix filled with zeros. That is even more boring than the identity matrix, but we should acknowledge that that this exists, so that in case you come across it, you are not too surprised. But we don't need this for now, but we will need the identity matrix and see this in a moment. Now, with these transformation matrices, you may want many times you may want to describe them a bit further, and there's a couple of key metrics or key characteristics that you can use to describe matrices further. And I think one of the more important ones is the determinant. I want to cover two of these key characteristics here in this workshop. One of them is the inverse. The other one is the determinant. In the first place, the determinant describes when you do a linear transformation of some coordinate system with a matrix, then the size of, or the relative size or area that is spent by your coordinate system might or might not change. In simpler words, if I rotate my house, does the total area of the house change? No, it's still, if I rotate, it still has the same size. If I scale the house from the smaller house to the bigger house, does the size of the house change? Yes, it becomes bigger. It's 2 times bigger in X, it's 2 times bigger on Y, so it's the total area is 4 times as much. If I do this stretch operation here in the middle, and I only double the X coordinate, yeah, then the area of the house doubles as well. And if I do the share operation and only move the thing gently to the right, the thing looks different than before, but the area does not change. Now, the determinant measures that. Yeah, that for every linear transformation matrix, I can calculate a determinant that might, that will tell me by how much the area will change. Now, there's 2 things to note by about the determinant. Yeah, we are dealing here with some easy cases. Yeah, one of them being that the size does not change, the other one being that the area goes up or down. There are 2 special cases that that one needs to be aware of. And this is a hint that the determinant does a little bit more. The special cases are the determinant can be negative. And this is completely unintuitive. Yeah. Why would, when I change, when I move a house around in a 2D coordinate system, how can the area change be negative? So it turns out then that in a vector space, if you make a house in a vector space, it has, from the point of view of linear transformations, it has a front side and it has a back side. And I could have a linear transformation that flips the whole thing from the front to the back. Yeah, let's say I rotate this around the y. I flip this on the y-axis, then the back side of the house would be on the front and the front in the back, even though we do not see that. Yeah, but the determinant catches that kind of behavior. Yeah, so if you see a negative determinant, this will tell you that I actually reversed the coordinate system. The other part is even more intriguing. The determinant can be zero. Yeah, like let's say I somehow flatten my house image onto the y-axis so that it disappears completely. Yeah, that would be an operation with a zero determinant. And if I manage to flatten the house so that it has no area, then I get a determinant of zero. And that is a very, very central property of matrices. Many times you will want to know if your matrix has a zero determinant. Yeah, because that means that certain things in machine learning, they are not possible then anymore. Good. Determinants are if you have a two-dimensional matrix, a 2x2 matrix, the determinant is fairly easy to calculate. You basically subtract two products. In all other cases, it gets super complicated. Yeah, and calculating a determinant from a big matrix is actually computationally expensive. So so fortunately, we don't have to deal with this. We are going to use a NumPy function for that. So let's apply some linear transformations. I'd like to switch to the linear transformation notebook. Look at some examples, and then we take a 15-minute break. I'm not seeing any questions right now. So what do we have here? In this notebook, we are defining a vector with an x and y coordinate, and we are going to interpret that as the hand of a clock. So I put here a little piece of code that draws a clock, and we have a vector x0 and 2y that is the hand of the clock, this blue line here that is currently pointing up. And what I want to do is to use different linear transformations to move the hand of the clock. And so first thing is that we can try here is to define this 90-degree rotation matrix that has a 1 and a -1 in the opposite corners, and the diagonal is empty. So you define that, and then you can use the dot product to create, to apply the transformation. Here again, the order is important. Yeah, because the matrix is a square matrix, I think it would still work if I swap the arguments, but I think then it would do the rotation in the other direction. So if I run this, my vector gets modified, and I can go up here and run this plotting code again, and I see, okay, the 90-degree rotation has moved the hand by 15 minutes, which is exactly the time that our break is going to last. So I can do this whole procedure again. If I run this dot product again, my rotation matrix is already defined. So I see now it's after the third dot product, no, sorry, the second dot product, I should see that it has an x of 0 and a y of -2. So it's pointing downwards, and so on. So we can rotate the clock hand by other angles as well. And for that you need to know that the trigonometric functions, they use the angle in radians, so not in degrees. So we need to convert that first. Let's try a 45-degree angle. So I'm overwriting the rotation matrix and apply that with the dot product and see how the plotting changes. And we see, okay, this has moved the vector around by 45 degrees. Yeah, and now seeing that that we can modify the angle in different ways, this gives us a training ground for playing around with these linear transformation matrices a bit to get a feeling for how they behave. Yeah. For instance, here is a stretch matrix. Yeah, it has the diagonal has a factor of 2. The other numbers are 0, so this should really scale the hand, make it twice as long. And if I run this and look in the picture, I see, okay, there is a longer clock hand. It might be that it doesn't show if we make it even longer, but you could try to put in a 0.5 here and then make it shorter again. Here there is a share operation that's where one of the coordinates stays constant, the other one gets modified. Yeah, here this is an operation that makes a bit less sense with a clock, but still it gives us an idea what is happening. Here we have the clock hand before the share, and after the share, we are stretching it in the x direction, so it goes a little bit out of the screen. But in the y direction, it stays the same. And finally, we could project the entire clock hand onto the x-axis and make the y coordinate go away. If I dot product this, there's a dot product. I have to write the dot product here. Let's look how my vector looks like. So I'm left with an x coordinate and my y coordinate is 0, and the clock hand is now horizontally flat. So we see that we can use multiplication with matrices in different ways. They are all called linear transformations. This helps us to move the clock hand around. I have an example with a second hand, and we should also calculate some determinants from it. But I think I'd like to save these for after the break. Take some breath, and we are going to resume our workshop at 11:18. So thank you very much so far. Welcome back. So we are in the section on linear transformations. This clock example is, in my opinion, this is a training ground to try out what matrices do and how to understand them better. The reason I created this because I wanted to have something where you can try out with basic properties like rotation or scaling with the most simple linear transformation possible, and that is a 2x2 matrix. That is a good starting point. I, however, wanted to show that it's possible to make linear transformations with larger examples as well. Yeah, so for instance, if we want to add a second hand to the clock, yeah, if we want to have a second hand to the clock, we need two x coordinates and two y coordinates. So we get a vector with 4 numbers. Yeah, so we have here x1, y1, x2, y2. And to draw that properly, we need to add an extra line to the code block that is plotting the clock. I'll insert that. Where is that? Here. And we should see that now the clock has 2 hands. Now the question is, how can we can we use linear transformations still to move both of the hands? Yes, of course we can. And I have a single example here. You might want to align that a bit on the screen in order to understand it a little bit better. I'm moving here the corresponding positions on top of each other. So you see that there is a top left square that is the rotation of the blue hand of the clock, and on the bottom right you have a rotation for the for the shorter for the other hand. Yeah, so we have a rotation of a vector of size 4, and that has to be a 4x4 square matrix. So if I apply that, we should see that both of the hands are moving, but both of them are moving separately, each by a different angle. Yeah? And that is a simple example of a rotation of a with a 4x4 matrix in a higher dimensional space. Feel free to analyze to experiment around with the numbers that you can put in here. Now, I said before the break that there's a very central property of matrices, and that is the determinant. When we talk about matrices that move around graphical vectors, you can interpret the determinant as how would the area of some object that you are transforming change by the transformation. The determinant is giving you a factor. And just to have here some examples of the determinant. The determinant does more, but let's keep it to this. So with a rotation, the area should not change. So our determinant of the rotation matrix is 1. It's not exactly 1 because there is, with trigonometric functions, you very often have like issues with floating point precision, but for all practical matters, this is a 1. If we stretch the if I have a matrix that stretches the space, so it doubles everything, the determinant is 4, because if I double the x-axis and I double the y-axis, then the area changes by a factor of 4, and the determinant gives me that. The share operation that we have here had an area of 1, so it's kind of distorting the thing a bit, but the area doesn't not really change. And the collapse operation here that makes the y-axis go away, I think that is the most interesting one, because this one has a determinant of 0. Whenever you see a determinant of 0, it means that some axis in your vector space is going to disappear. It's not necessarily one of the unit vector axes, but some information from your original vector is going to be lost. So, and that is something that makes the determinant something very important in linear algebra. It tells you, is my matrix, if I multiply something with my matrix, am I losing information? Yeah, the determinant is giving you a precise result on that, and that is what makes the determinant a very important tool. I'd like to move to the next chapter, which is something that we have not covered so far, is the question of distances. This is, I hope, a little bit easier. Yeah, because we so far have seen vectors, we have seen matrices, we have seen square matrices. I think this is the backbone of linear algebra. The rest is practical applications. But we have to look at, before we move on, how you would compare vectors, because that might be necessary for the other things. And this goes by the title Distances and Norms. And I start this chapter with a little bit of eye candy. Yeah, one of my favorite data sets is a data set that contains 333 penguins. They are all there with their body weight and the length of the bill and other numbers. And I created something called a distance matrix. And in this chapter, I would want you to take away how to create something like this and what it actually means. It's not that hard. Yeah. So because what we want to do is compare two vectors. If you think about it, you can translate the question is, how can we compare two penguins? And if you can compare two penguins, you can ask, how can I compare two entities of anything? Yeah, whatever data you are working with, how can you compare two data items? That is what this chapter is about. So here's the penguin data. Yeah, each row is a penguin. We see, and this is a pandas table. We see that some of the columns, they contain words. I'm going to ignore the words completely for now and focus only on the numerical column. Yeah, we see that there's the length of the bill, there is the depth of the bill, that is how wide it is, I think. There's the length of the flippers of the penguin, so the wings, if it was a flying bird, and the body mass in grams. And what we basically want to calculate, how far away from each other are two penguins. And I want to introduce 3 different metrics that allow you to do that. That brings us, that kind of thing brings us a lot closer to what I would call everyday data science. Yeah, so we need something called norms and we need something called cosine similarity. The simplest thing that one could do is we take the difference in the bill length and the difference in the flipper length and the difference in the body mass, and add them all together. Yeah, that is something called the Manhattan distance. If we abstract that a little bit and say our penguins are basically arrows in a coordinate space, then we would say we calculate their distance, the distance between both vectors in the x space and the y, in the x dimension and the y dimension separately, add them up. And because such a difference can be positive and negative, the formula has the absolute operation here before the inside this sum. And this whole thing, the Manhattan distance, is also called the L1 norm of a vector. Yeah, so if I calculate a vector that is a minus b, and I take the L1 norm of it, then it's still an L1 norm. Now, this in principle works in not just in a 2D space. It also works in a 3D space, in a 4D space, in a many-dimensional space. In a many-dimensional space, there is a question why that might be more difficult. In a many-dimensional space, you usually very easily have some of the dimension that is that is dominating the others. That is simply more likely. It's basically a matter of statistics. Yeah, that the distance calculation in higher dimensional spaces gets a bit trickier, because you usually it's more likely that you have something that distorts the result. Yeah, so here in our penguin data, we have the body mass, yeah, that that is 100 times higher than the other numbers. We will have to see what we do about that, yeah, because we don't want the entire distance between two penguins to consist only of their weight difference, because there might be other important things. Yeah, but you get problems like that in a lot more when you are moving in a higher dimensional space, and that is why you at least need several different distance metrics to choose from. So the Manhattan distance is probably the easiest. The second easiest is the Euclidean distance. But the Euclidean distance has the advantage that I believe that all of you already know it, because that is what you learn in school when you have the Pythagorean theorem, when you have a straight angle triangle and you want to calculate the length of the hypotenuse of the longer side of the triangle. You say c square equals a square plus b. No, sorry. Yeah, c square equals a square plus b square. If you move the square on the other side, you get a square root. And if you then do the same thing for more than 2 dimensions, you arrive at an equation like this. Yeah, that you sum up squares, or the square difference for every dimension. And then take the square root. So if I calculate this vector a minus b, take the square root of every component of it, and then take the square root, I have the Euclidean distance, or the L2 norm. Yeah, and the L2 norm, because of the square, it puts a higher emphasis on bigger differences in some of the dimension. Yeah, that is why it differs from the Manhattan distance. that is so. So sometimes you may want to use one, and sometimes you want to use the other. I find the L2 norm a bit more prevalent in machine learning, in particular in something that is called regularization. Yeah, like when you do machine learning and you want to what a common problem with machine learning is something called overfitting. That is when your machine learning model is learning too much. Yeah, that leads to all kinds of hallucinations. I think if you've been using any large language models, then you've seen hallucination, and the idea goes a little bit into the same direction. And what people do to counter that, they tell the model, hey, please only focus on the most important stuff. That is called regularization, and it's done using the L2 norm, adding an L2 norm as a penalty. But you can use it for pretty straightforward distance calculations between items of data. Question. There's a question about how is the overfitting approach we learned yesterday different from this approach. I don't know what overfitting approach you are you learned yesterday, but classically there's a couple of different things that you can do against overfitting. The top three ones that come to my mind is put in more data. Second, make the model more stupid, basically. And the third one is all kinds of regularization techniques. So if you were doing some standard stuff on machine learning, I would assume that you used something like a training test split and calculate some training and test scores. And that is what people do to find out whether there is overfitting in the first place. And then you add regularization to make the overfitting go away. Now, how you do regularization differs a bit from what model you use. There's a lot of different techniques, and adding an L2 penalty is one of them. I think it's more popular with linear and logistic regression. Feel free to add anything to the question if you'd like me to elaborate on that point. There is a third distance metric that is quite different, that is called the cosine similarity. And the cosine similarity is, I think it's a very robust metric. It works in high dimensional spaces. Yeah, so which is why when you have a lot of, if you have very high dimensional vectors, you usually will find that people try the cosine similarity first. So it measures the angle between two vectors. More precisely, it measures the cosine of the angle. That means if the cosine is 1, you have a perfect match. So if two vectors are equal, if two vectors are equal or pointing in the same direction, the angle is 0 and the cosine of 0 is 1. So 1.0 means perfect similarity. If there's a 90-degree angle, then the cosine is 0. And if you look at the equation, you find that there is a dot product. So the dot product of two vectors is directly proportional to the cosine. Yeah, and that is kind of a proof it's kind of a proof that if your two vectors are orthogonal, then, and your vector is 90 degrees, with 90 degrees, the cosine is 0. So the dot product of two orthogonal angles has to be, of two orthogonal vectors has to be 0 as well. This cosine formula is highly important nowadays. Yeah, so classically it's used for stuff like clustering and anomaly detection, and it's also being used in some recommender systems. Like, let's say, I don't know, I have a user profile on let's say on Netflix. I know what users they watched, and I want to find a user with a similar taste to get them useful recommendations. I can use the cosine similarity to calculate the similarity of two users or two movies if I wanted, even if I have a lot of them. The cosine similarity has been heavily used in the recent 2-3 years in the field of artificial intelligence. If you heard about something called RAGs, that is basically a search-powered chatbot. So, and cosine similarity is used for the search part. So let's say I have a database of text snippets, and I have a question, and I want the chatbot to look in the database to find which text piece answers the question most likely. You can use cosine similarity to find the piece of text that is most similar to the question, given that you have a way to convert text into numbers. So there's directly a question on that. Can you elaborate how cosine similarity is used in retrieval augmented generation in practice? I believe that is pulling files and information for an LLM from a vector library. Yes. So there are 3 steps. Yeah. So let's say I have a database of texts. Let's say, what could I store in a text? Like I don't know. Let's say I'm building a help database for a software product. I have text pieces, and I put them in a database. The first thing that I need to do is convert every text item into a vector. Yeah, I'm not elaborating on how to do that. Yeah, there's out of the box solutions for that. If you want to try out one, look for Olama embedding. I'm putting the term in the chat box. Yeah, that is a machine that takes pieces of text and converts them into vectors. Then you can store these vectors in a vector database, or you could store them in a pandas table if it's a small amount of vectors. Then you do the same with your query, the question that you get. You also convert that question into a vector. And then you basically take the vector for your query and calculate the cosine similarity to all the vectors in the database, and take the similar one, the most similar one, and then tell the large language model, build me an answer based on this text. That is how retrieval augmented generation works. It's not rocket science. Yeah, the cosine similarity is an easy, straightforward function. You can do the same for sentiment analysis, by the way. Yeah, that if you have an example set of, let's say I'm collecting text reviews of hotels, for instance. And I have labeled some of them as good reviews and bad reviews. And I have some review and I want to know, is this a good review or a bad review? Take the text, make numbers out of it, calculate cosine similarity, see, is it more similar to the good or the bad reviews? Yeah, so that's usually a cosine similarity thing rather than Euclidean or Manhattan. Some takeaways. So we have multiplied vectors, we have multiplied matrices. We have seen that matrix multiplication applies linear transformations. We have seen the determinant, and we have seen that the length of a vector or the difference between two vectors can be measured by the L1 and L2 norms, or the Manhattan or Euclidean distance. These are different words for the same things. Cosine similarity is a little bit different because it measures the angle, not the distance. Yeah. But I think these three are the most important distance metrics for linear algebra. There's a couple of more. Yeah, for instance, if you work with geocoordinates, none of these work. Yeah, because the Earth is not flat; it's a ball. If you have like very long vectors of binary numbers, you might want to choose something different. But for most these three, they work. One of them works for many cases. Good. Let's look at the practical side of it. I think I have a small exercise for the distances as well. This is using my favorite data set, the penguins. So let's calculate some distances between penguins. So the penguins, they come from a library called Seaborn. I think Google Colab should have it. Yeah. And the link just went into the chat box. Thank you, Hui. And this is a great data set because you can literally try out every data science tool on it, and it always works. And it's small and fast, and the penguins are cute. So this is a very good training. It's a very good training ground. I love it too. So this time I only want to use the numerical columns. So I'm using a little pandas phrase here to select 4 columns from it, the ones with numbers, and put them into a matrix X. Technically, this is a pandas data frame, but I call it a matrix because it's a table with numbers. Note that because I select multiple columns, I need to use the double square bracket here. And then we can calculate Manhattan distances between penguins because we now have only numbers. Yeah, so I wrote a function here that takes 2 penguins A and B, or 2 vectors, takes their difference, takes the absolute, sums up everything. It's a piece of cake. Yeah, you could import a Manhattan distance function, but I thought it might be illustrative to see this in NumPy code. And then I could take the first penguin that has here an index 0 and the second penguin and see what distance they do have. And I have get a distance of 56.7. This doesn't tell me much, yeah, because the distance here, it does not have a useful unit because it's a mixture of different columns. Yeah, this only makes sense if I start calculating other distances. Like if I see if the Manhattan distance to penguin, to the third penguin, is it bigger or smaller? I could check that. I could run this as well. Oh yeah, it seems that the third penguin is quite different than the second one was there a... Oh yeah, it's 10 times further apart apparently. Yeah, so this kind of stuff you find out with the L1 norm. Then I can do the same with the Euclidean distance. The difference is not that big. The difference in the Euclidean distance is that we get a square root here and a square here. Yeah, can we run a Euclidean distance between the two penguins? Yes, I need to call the function, of course. And we get different numbers. In any case, we must not compare the Manhattan or the Manhattan and the Euclidean distance directly. They are not comparable, but I can compare two penguins. So I see the second and the third penguin is still further away, also with the Euclidean distance. Yeah. Then we can calculate a cosine similarity. The function for that is a bit longer because we have to calculate here the L2 norm at the bottom and multiply the two norms. This is a normal multiplication because the norm gives you a number. It's a scalar, not a vector, but we have the dot product here on top. And if I calculate the cosine similarity, then I should get a value between 0 and 1. If I put in, and I see here that I get numbers very, very close to 1. This is a bit unsatisfying. Yeah, I would expect that I see a difference when I when I see when I put in the third penguin, of which I know that it's further away, and I see a difference here in the 5th digit. This is a bit fishy. What is not fishy is if I compare a penguin with itself, I get a cosine similarity of practically 1, which is the best thing that the closest similarity that we have. But this high amount of 9s here, this is something that I don't really like. And this points us directly to a problem. Yeah, when we calculate these norms and distances, is the body mass of the penguins. This is dominating too much. Yeah, it's on a completely different scale than the other measures. Yeah, so they are not. These are not comparable. The body mass will dominate everything, so it's the only thing that matters. So it's basically ruining our calculation. So we need to normalize the data or scale the data. And here I'm going to do something, the most straightforward normalization that there is, that is we convert all the numbers to values between 1 and 0. That is called min-max scaling. So we do this for every column separately. I'm doing this here, so our penguin data should be changing a bit. Wait, my notebook was hanging for a second. If I look at my scaled data for the first 3 penguins, I see that it still looks like a table, but now all the numbers are between 0 and 1. 0 meaning if here we would have a 0, this means this is the shortest flipper length that we found. And if there is a 1 here, it means this is the heaviest penguin in the data set. Yeah, so and now we have comparability across the columns. If I now calculate the distances and similarities, I should see that this difference between the penguin 1 has a similarity of 98. This one has still a 93, and if I take penguin number 300, oh, this is a very distant penguin, so this should be quite different from the other two. Now, what can we do with this? Now we are getting closer to practical applications. Yeah, so we are getting to the butter on the cake. So one of them is we can search for similar penguins. Yeah, so if we put in some numbers, I'm using here the scaled numbers. We are looking for a perfectly average penguin. We basically loop through all the penguins, calculate the distance. I use the Manhattan distance here and return the most similar penguin. So this is the most average penguin in our data set is some penguin with a 42.9 millimeter bill in the face. So so what we have here is basically a 10-line implementation of the same mechanism that powers a retrieval or augmented generation, only with penguins instead of text. What is nicer is that we can calculate, if you, instead of doing prediction, we could calculate the distances of all penguins with all other penguins. Yeah, that leads us to a special type of matrix that we call a distance matrix. So I have a loop here that calculates the Euclidean distance of all penguins against all others. And I think that should give us a heat map here. There we go. This is our heat map. This is showing us the similarity of penguins. So now we can explain that every pixel here in the heat map is a Euclidean distance. I think I took the I took here 1 minus the Euclidean distance, so that the higher similarities get the brighter color. So I converted the distance matrix into a similarity matrix. It's a small math trick. And now we can look here. Do we see any distinct groups of penguins? And because the data is sorted by species, you can see, okay, we have quite a clearly separated group here in the bottom right. These penguins are close to each other. They are very similar to each other, but they are different from the rest. And then we have two other. So how to read the similarity matrix? Every row is a separate penguin, and every column is also a separate penguin, and they are the same penguins. So this is why on the diagonal we have this bright white line. These are the penguins compared with itself. They are, of course, perfectly similar. Yeah, and then we see that these squares here. These are the three. These are the three separate species, and then we have this red shaded area that tells us, okay, the second species is a bit similar to the first one, so there's a bit of overlap. So it's 3, not 5. This area is not a separate species. It tells us that the 1 and 2 are similar. We have a question. Why is it important to ensure that all features are comparable before calculating distances or similarities? Very good question. Because you do not want to make the comparison by by the order of magnitude. You basically you need to decide how do I want to account for the weight, and how do I want to account for the bill length, even if the weight is 100 times bigger. Yeah, if I do the same thing and use only the unscaled values here, then I should see. Then I don't see anything. Why? Because the scale is off. Then the differences, they are much less pronounced. So I'm basically diluting my information, because the only thing that my similarity is now going to look at is the weight difference. And that does not tell us everything that we would need to know. Yeah, so it's the point of making the features comparable is to make sure that all of them are taken into account. So the distance, a distance of similarity matrix is a starting point for many clustering methods. Yeah, so I can take some graphic like this and see if I can like automatically identify here these groups of similar penguins. And this is what clustering methods do. Here's one example: the using something called k-means clustering. It's directly based on the Euclidean distance, and what we see here, it labels groups of penguins here in the plot. Now, this one did not work very well. Why not? Because all we see, it's making a horizontal separation by the body mass. So we have here a cluster of very light penguins, medium-sized penguins, and heavyweight penguins. And it doesn't do anything with the bill length. Yeah, that is what happens when you use unscaled data for clustering. If we, however, use the scaled data, we should see that it makes some more reasonable assignment of groups. So this group on the bottom left gets clearly identified. This orange cluster gets clearly identified. Those on the top as well. There's some penguins here in the middle where the algorithm doesn't really know. These are kind of hard to classify. Yeah, so this is a nice aspect of this data set, that it's not entirely trivial. Yeah, so scaling is important, especially when calculating distances. Because if you don't do it, then you might end up losing information, or information that gets excluded from the distance calculation, or it gets pushed to the less important decimal places. Good. I hope it answers your question. We have another question here. Does the plotted matrix look like this because the penguins in the dataset are already sorted by species? Yes. There's Adelie penguins, Gentoo penguins, and chinstrap penguins. I don't know in which order. How could we create a readable plot with a dataset where the penguins are not sorted in any way? This is a great question. Sometimes these distance matrices, they look very messy. Yeah. So you might want to come up with some way to sort it first, to make sense out of the matrix, to see whether there is any structure. Yeah, so oftentimes it helps to sort to take some feature to sort it by some column that you have. Like, let's say we could sort the penguins by bill length and see if we recognize any of these squares here in the distance matrix. It's not necessarily easy to interpret, but it's a good way of seeing, hey, there is a special kind of matrix behind clustering that is called a distance matrix. And it also may help you to see, is there a pattern, or haven't we found anything yet? Good. We have about 1 hour left. I would like to take the time and work through a couple of practical examples. I'm basically done with the theory. So we've seen. Let's see my mind map here. We have seen vectors, matrices, and square matrices. So far, with square matrices, we saw one type of square matrices to do linear transformations, and now we saw also the distance matrix that is also a square matrix. We calculated distances. Now let's see what else we can do with it. Let's see how many of these we can get covered. And I would like to start. Next one up on my agenda should be the recommender system. It's kind of a classic. This image did not make it into Google Colab. If you want to get back to it, make a screenshot. It's also on the academics page in the material. It's there, so it's not lost once it scrolls out of the screen. I want to build a movie recommender in 10 minutes. Yeah. We need for that, we need a matrix. We start with a matrix that contains movie ratings. Let's see how a matrix of movie ratings looks like. I have 5 movies. That's a small, I have a very small movie portal. Yeah, I have only 5 movies, but they are Titanic, Barbie, Shrek, Dune, and Star Trek. Now, the Star Trek fans might object, hey, Star Trek is not a movie, it's a ton of movies. I don't care today. I want to build a movie recommender for 5 movies. I also have 5 users. And some of the users have seen movies and rated them. Yeah, that gives me a matrix here of ratings. Every row is a movie, and every column is a person. Yeah, 1 means they saw the movie and didn't really like it. 5 means they saw it and they think, hey, it's the best movie ever. None means they did not see the movie or did not rate it, at least. And now I basically want to use this information to give recommendations for the missing values here. I basically want to predict the values for which we don't have any data yet. There are many different approaches that you could do. One could, for instance, take I don't know, ask what is the most similar movie to Dune based on the user's ratings or something like that, and use cosine similarity for that. But this is not what I want to do here. I want to use a concept called matrix factorization. Yeah, so I want to build 2 other matrices. I call them P and Q, and they add genre information. So I'm doing this manual. Normally you would do this using an automated algorithm. You find the code further down below that does this automatically. But to understand what is happening, let's do this by hand. I want to put here numbers that tell how much of a drama movie is Titanic. It's a 5. Then we do how much of a sci-fi movie is Titanic. It's a 1. Then we do the same for Barbie. Barbie gets a 4-1. Shrek is, I don't know what it is. Shrek is not a sci-fi movie. So it gets a 3. Dune, yeah, Dune is definitely a sci-fi movie, and it has also a bit of drama. And Star Trek has a bit less drama, and it is also a sci-fi movie. And that gives us a 5-row, 2-column matrix. Now we do the same thing for the users. We describe how much each of them likes each of the 2 genres. So Bashir is much of a drama fan, but doesn't like sci-fi. For the third user, it's the other way around. They are heavy sci-fi fans. So the first row is now for the drama, and the different columns are for the users. Our fourth user likes drama and a little bit of everything, so I put in a 5-3. The last one did not like drama, but sci-fi from the little ratings that we have here. And this gives us a 2-by-5 matrix. So we have a 5-2 matrix and a 2-5 matrix that calls for a matrix multiplication. Let's go to the picture and see what we want to do here. Yeah, we have constructed these genre matrices P and Q with the help of our ratings, and they have this hidden dimension. This is the number of genres that we just invented. And if I put this user matrix on the left and the movie ratings on the top, then I can do a matrix multiplication and reconstruct this rating matrix here in the middle. So I take 2 matrices to make a bit bigger matrix out of them. That is the idea of matrix factorization, that I take this rating matrix, separate it into 2 smaller matrices, and then put them back together later again. So what I do here is I use a dot product of the 2 matrices. I can do this and get a rating matrix. I'm going to normalize this so that the numbers there have a maximum of 5. And now I can compare this matrix to the original one. I basically want to use the Euclidean distance, only that when I do this for matrices, it has a different name. It's called the Frobenius norm. Yeah, so it's basically taking the square distance. So I take the difference of the 2 matrices. I want to use this to measure how well did we reproduce the original matrix, and I get some number. I could use this as a way of as a tool to optimize. So if I go back here to my matrix Q and I say, maybe this user doesn't like drama movies, even less, and I rebuild the whole thing again, the numbers change a bit, and I can use this Frobenius norm from my 2 matrices to see if it gets lower, my matrices are more similar. Yeah, then I can throw a machine an automatic optimization algorithm on this and say, play around with the values in P and Q automatically until this distance gets minimal. So this Frobenius norm, this is really the same as the Euclidean distance or L2 norm, only that we apply this on a matrix. And then what I can do then is I take at the values from my reconstructed matrix and see, and here I have my predictions. So if I look at Elena hasn't seen Barbie, Shrek, or Star Trek, but based on the data that we have, we would see, we predict that Elena would give a 4.5 to Star Trek. So maybe that would be a good movie recommendation in that case. Yeah. That is a very handy application of matrix multiplication. It's called matrix factorization because all you need for it is this original rating matrix that we started with here. The scikit-learn library here that we have here basically does this automatically. We don't have to do anything. I only have to decide how many genres I want to allow for. The more genres I allow the NMF algorithm to invent, the more precise my my predictions are going to be. But also at some point, the system will start to hallucinate. Yeah, so there's a trade-off here. So I can run this, and then I also get these matrices P and Q, this time automatically optimized ones, and I can use them to, whoopsie, what did happen? Oh no, wait, there's a bug. Here it says fix a bug. This is what happens if you put wrong shapes together. I get a useful error message from pandas that says I was actually expecting a 5x5 matrix, but you gave me a 2.2 matrix. What you do in such a case, first thing is you look at what the shape is. And we say, hey, we don't want a rating matrix of 2x2 because we have 5 movies and 5 users. Yeah, so we did the dot product the wrong way around. This has to be a P times Q. Now it's correct, and we can create a table that has all the predicted movie ratings. The numbers don't match very precisely, yeah, because here for Dune we had, I don't know what we had, a 4 maybe or a 5. And this is a lot lower. But all you want to do with this, if you want to make a movie recommendation, you want to find out what is the next best movie that you can predict, and it's still going to be Star Trek in this case. That's matrix factorization. Good. I found a question that I did not spot further about the k-means clustering. Is always the Euclidean distance used? No. You can basically use any distance metric for the clustering. Sometimes you use cosine, sometimes you use Manhattan, sometimes you use one of the other distance metrics that we did not talk about here. Thank you for the question. So this matrix factorization thing gives you a nice idea of how matrix multiplication is applied in machine learning, because this matrix factorization method is an actual machine learning algorithm. And it also gives you quite an insight into how recommender systems work. I'm I rather doubt that what Netflix and Google are doing these days is really using this matrix factorization technique as their main algorithm, because there's something like 15 years of research that went into this. So it has probably evolved quite a bit. But to understand what is going on, this is an excellent starting point, in my opinion. Let's look at another application. I have linear equation systems. I need to bring back the fruit example once more. This is a completely different corner of linear algebra. It's more, has nothing to do with machine learning. It's more of a classic. Linear equation systems. You have seen linear equation systems somewhere in high school math, I assume. If you have like multiple equations that say 3 times x plus 2 times y minus 3z is 5, and then you have a couple more equations like this, and then you have to move around coefficients to find out the exact values of x, y, z. We can do that with linear algebra as well. Example. Yeah. I have 4 persons. They are now done with watching movies. Now they are hungry and go food shopping. Yeah. We know what they bought. We know how much they paid. So in this last column of the table, we have the amount of euros that they paid. Yeah. But we don't know the prices in the shop. So this is unknown. And this is what we can treat as a linear equation system. Yeah, like the numbers of fruit would be the coefficients of our variables. So for Ada, it would be 2 times apple plus 0 times banana plus 4 times cherry plus 2 times grapes would be 24, because we know Ada spent 24 euros on fruit. And the same for the other 3 people. They must be quite hungry, or they have a lot of other friends around that we don't know about. So in a nutshell, we have 4 equations and we have 4 unknowns. Yeah, that is a situation where we can use linear algebra to solve it. We could also do this manually, but linear algebra gets the same thing done faster. Yeah, so the first step would be that we take the table and make a matrix out of it. Yeah, if you have 4 fruit types and 4 people, we make a 4 by 4 matrix out of it. And we also need to put the total prices into a separate vector. Yeah, so that is all done here. Now, what you might want to think about when you do this is to check first whether this linear equation system is even solvable. Yeah, like we want to know the prices for all the 4 food types, but if nobody bought bananas, we will never find out the price for bananas. Yeah, that means that the equation system is not solvable. And there are 2 ways how to find out whether a linear equation system represented by a matrix is solvable. One of them is something that we have already known, and this is where linear algebra starts to get very interesting, and it's the determinant. Yeah, so the determinant actually tells us if a linear equation system is solvable. That is, if it's non-zero, that means that means that it is solvable. If the determinant is 0, the matrix is special. Yeah, then we have a situation where it's not solvable. Another option would be to check whether the matrix is invertible. Yeah? Invertibility is a nice property. You can calculate, we have here a function that creates an inverse matrix. This is the inverse of the matrix. The numbers don't tell me anything, but the inverse matrix has the property that if we multiply it with the original matrix, then we should receive an identity matrix. Can we see an identity matrix, please? Okay, my notebook is hanging for a moment. Okay, now it came back. So if I multiply the matrix with its own inverse, I get an identity matrix that only has values along the diagonal, everything else being 0. And that is not possible with every matrix. The cool thing is, if it's possible to create such an inverse matrix G, we know that the linear equation system is solvable. Yeah, and when that happens, you can use something called Gauss elimination or Gauss-Jordan elimination that basically is an automated way of doing the thing that one would do manually on paper, that you resolve that you substitute your variables in such a way until you are left with one, and then you work your way back through the other equation. In NumPy, this is a one-stop function. So you basically say, here is my matrix, here is the amount on the bills. This is the vector that should come out of on the right side of the equation. Give me the prices for all the food. There we go. One important thing when you do this is because this matrix is a square matrix again, it's quite possible that you mess it up. If I take the transpose of F, I can still solve a linear equation system, but I get BS results because I have some negative numbers. Yeah, so they don't make any sense. Yeah, will I get money back when I buy cherries? No, it's doing the same thing. I might want to double check by taking a dot product with my matrix of food shopping and the prices, and I should get the numbers on the bills back. Now, please note that not all linear equation systems are solvable. Yeah, the inverse and determinant, they tell you if that is the case. So for instance, if we have a matrix where nobody bought any bananas, here is one. That banana column is 0. That inverse function is going to give us an error and say, no, this is not possible. This is a so-called singular matrix. It's not invertible. Yeah. Likewise, if we calculate the determinant, we should see that the determinant is 0. So these are two ways to find out that, or to prove that the linear equation system is not solvable, and we don't need to even try. It saves a lot of work. Same thing happens if you have a matrix where you have rows that are collinear. That means they are pointing in the same direction. So let's say if I have someone who bought 10 apples, 10 bananas, and 10 cherries and paid €100, and I have a second person who bought 20 apples, 20 bananas, 20 cherries, and paid €200. This third row here, this doesn't give me any additional information. It's collinear to the other one, and that again gives us a singular matrix. So this would give us an error message, and the determinant would be 0. Sometimes it's not easy to recognize when a determinant is 0 and when not, but this is why I find these functions quite handy. I added a piece of code that visualizes the food shopping as a bar plot, just as a nice nice extra example of visualizing a matrix. You can visualize matrices as bar plots as well if the number of rows and columns is not so high, and you have some labels that make sense for it. Good. What I presented here is kind of an easy case of a linear equation system. Yeah, because we have exactly the same number of rows and columns. It gets a bit trickier if you have, let's say, if you have more people and you don't know which of them you need, you will have to use something called the rank of a matrix to find out that how much redundant information you need to eliminate first. Another thing that is that we don't have we have a precise match here. If we have like this does not include any errors. So if we have like imprecise information, you may want to use something like linear regression instead. So that would push that kind of data a bit more in the direction of machine learning. If we have something that is not exactly a linear equation system, but is similar, like if we have some, instead of the equal sign, have something else, like we say, we want this total sum to be smaller than 24, and we want to solve an optimization problem, then we would need to use a different type of program. I have put a couple of links here at the bottom, and the one, if you want to are more interested about the subject, then I highly recommend to you to try the burrito optimization game, which is made by the Gurobi company. It's one of the better known manufacturers of linear optimizers. So Gurobi is a program that you can use if you, let's say, you want to calculate timetables for a public transport service and create the timetables as such that the time that you need to take to switch from one bus to the other is as short as possible. Yeah, and also to avoid, I don't know, congestions of buses in the same place. That is a type of problem that you can solve with a linear optimizer, and Gurobi does that kind of thing. And this optimization game, it's basically a mini tutorial that gives you a very good idea about what kind of things you can do with this type of software. So it goes a bit, quite a bit beyond what we did here with the linear equation system, but it's using a similar starting point. So it's an important area of application that is not machine learning. This is why I included it here in this tutorial. Let me check if there are any questions in the chat box. No, I'm not seeing any. I have one more. Graph analysis. So I have to apologize for putting in this graph. Yeah, because it's hard to understand if you're not living in Germany, because the abbreviations, they don't say anything. This is a graph that I drew manually. Yeah, it's not computer constructed. What we have here is a simplified representation of the federal states of Germany. In Germany, we have 16 federal states, and some of them, they have borders in common. Yeah, for instance, we have here on the right side, this is Berlin. From Berlin, you can only go to the state of Brandenburg, because we are an island in the middle of it. But from Brandenburg, you can go to 4 different places, and so on. Yeah. So this maps basically the adjacency of all 16 federal states. Now, in the first place, you might wonder, hey, what does this have to do with linear algebra? It's a graph. It's not like a vector or a matrix or anything. And what I want to show you is that, yes, also in this area we have matrices and vectors around, where we will see more of them. What I want to analyze is which of my 16 federal states is the most relevant traffic-wise, like through which of them would most people travel. Like, assuming I'm simplifying here, yeah, I'm assuming they all have the same size and the same number of people inside, but that's a valid simplification here for a workshop setting. And the way I want to approach this is I will take a person that's a traveler person that starts somewhere, let's say in Berlin, and then they travel randomly. Yeah, they say when they are in Berlin, they travel here to Brandenburg, because that's the only place they can go. From Brandenburg, they would roll a dice and then travel, let's say, to the north, to Mecklenburg-Vorpommern, and then to Lower Saxony, and then they move around. And I want to know, if they do this for a while, where would they most likely end up? Yeah, that is a way to measure how relevant or how central some parts of my graph are. And let's see if we can find a matrix and some linear algebra concepts in this. So the first thing that I do here is I create my graph. I have the graph here as a Python dictionary. I had this written by ChatGPT, because ChatGPT knows a bit of Python and it knows a bit of Germany. I did not really check it. Yeah, so it comes with a caveat: don't use this for a real world project because it's not double checked. And this is not a matrix yet. But what I can do with this is I can implement this basic idea, that I have my traveler start in Berlin, and then let's say, let's do 1 million random steps that they check the connections from where they are and choose the next location and the next and the next. And I keep account on how many times they visited one particular place. If I do this 1 million times, it doesn't really matter. It doesn't really matter where I start. Yeah, there might be a small it's very small bias towards Berlin, but I'm ignoring this. And this kind of approach is called a random walk, or more generally a stochastic process, or the fancier term that brings us closer to linear algebra is a Markov chain. Markov chain is a state-based model. I'd say my traveler is always in a specific place that is the traveler's state, and there's a limited amount of places they can visit, and they are somehow connected. That is what makes a Markov chain. Let's see where our traveler ends up with. I get a list of counts, and I can make a bar plot out of these. There we have the data. And it turns out that, if I take this graph and all the connections are neutral, Berlin is not a very popular place. Yeah, because it's kind of hard to reach. But the random traveler travels very frequently through Lower Saxony because it's kind of in the middle and has a lot of connections. And through Hesse because it has less connections than Lower Saxony, but it's still in the middle. If we check these two in the original graph, it's these two. They seem to be travel-wise, they seem to be very important nodes in the graph. We might also check Thuringia, which is here, which I think would also be in the... Oh yeah, it's somewhere close up with Brandenburg. This approach here, it's a naive Python implementation. This has a flaw. Yeah, I'm basically doing 1 million dice rolls after another. This is very slow and it's not feasible for larger graphs. Yeah, I will lose the details. So I need to do something else to make this computationally more efficient. And what I'm going to do is I take my graph and convert it to a matrix. Can I convert this to a matrix? I'm calculating something called an adjacency matrix. It's a bit similar to the distance or similarity matrix, only that the adjacency matrix will only contain ones and zeros. Yeah, the one meaning, yeah, there is a connection, and the zero means no, there is no connection. And we can visualize that one as well as a heat map. Although it looks a bit less exciting than the distance matrix of the penguin, of the penguins. But we do see here, you can see that Lower Saxony. Wait a moment, I think, the white spots are the connections, the black spots are no connection. So now what can we do with this adjacency matrix? Now we can calculate a Markov chain model. Yeah, the Markov chain basically calculates steps for an infinite number of travelers at the same time. Yeah, we say that we have instead of taking a single traveler, we are using a vector that describes a probability distribution. And at the beginning, we say, hey, at the beginning, when we have 16 states, the probability of a traveler to be in any particular place is the same. It's 6.25% to be in any of the states. Yeah. And now we can use the we can use multiply these probabilities with a transition matrix. This is our adjacency matrix, but I think we normalized it. There it is. What did we normalize it to? I did not execute this yet. This matrix is normalized in such a way that the sum of every column is exactly 1. So I get the probabilities from Berlin. I have a 1.0 probability to travel to Brandenburg. From Bavaria, I have a 25% probability to travel to Baden-Württemberg. And every column is going to add up to 1. This is how a probability matrix looks like. And I take this matrix and calculate a dot product once again. So I do a normal matrix vector multiplication that would give me a new vector that with slightly adjusted probabilities. Yeah, so that I see where would my travelers end up. I do this for 10 steps, which is very fast to calculate. And then I see where do they end up, and I end up with practically the same result as before. Yeah, so the Markov chain approach kind of allows me to simulate the traveler behavior and I end up with pretty much the same thing, but I have only to do 10 matrix multiplications instead of simulating like 1 million random decisions. Now, what is this used for? Of course, you can use this Markov chain approach to simulate very complex processes. Yeah, so if you can represent them as a graph and you have some probabilities that that tell you how you would move along the graph, then you can use this method, and it's awesome. There is a very famous use case where this is being used. That is, if we scroll up to the graph, now imagine that instead of the traveling through a country example, every location here in the graph is a web page. And I then managed to simulate this Markov chain and find out which of the web pages are the most important ones, because many other web pages are connecting to it. That is an idea that has been used some 25 years ago by, I think, Larry Page and Sergey Brin to rank the outputs of web searches. And this turned out to be a lot better than what people used for the sorting before. So what we have here is known as the Google algorithm, or the page rank algorithm. That is the thing that has made Google a leading multi-billion or trillion-dollar corporation. It's an algorithm based on linear algebra, and it's not super complicated. Of course, if you want to do this not for 16 nodes but for the entire internet, it does get quite a bit more complicated, but it's doable as it was doable 20 years ago. They added a little twist to this approach. That is, they have a damping factor that is basically adding a small probability that your traveler would teleport randomly to a to a random location instead of following the path, that kind of makes the results a little bit better. I implemented a small example of that here. So this changes the result a little bit. So if we add a little bit of a teleportation probability, then the height of the bars, the size of the bars gets a little bit closer to each other. If we increase the teleportation factor even more, then yeah, the traveler will only teleport and not travel normally anymore. Then all the probabilities, they basically become the same. So one needs to find that the sweet spot for this number. Avery asked a question: are Google Ads an application of this? I believe that the Google advertisements, they are rather something built on top. Yeah, so the Google used PageRank to sort the primary search results. The advertisements, they definitely come from some other source. I think they do something that is closer to the RAG approach, that they take the query that somebody put in, make a vector out of the text, and use something like cosine similarity to find out whether they have any matching advertisements for the query. Also, I think that the original PageRank algorithm has evolved. So I think nowadays Google will probably use something more advanced. But the algorithm is still good, and I think it's one of the more important algorithms of all time. There is one concept in there that I think is in my understanding the door to the more advanced chapters of linear algebra. That is something called eigenvectors. Yeah, and eigenvectors and eigenvalues. This is something that really took me a very long time to understand, and it's something that cannot be explained easily in a couple of minutes. But I did not want to leave it unmentioned, yeah, because if you have a matrix and you interpret that matrix as a linear transformation, yeah, in a sense, our adjacency matrix that represents this graph of Germany is still a transformation matrix between coordinate systems. Eigenvectors, they are kind of the rotation axis of that linear transformation. So they show you some central or important properties of that matrix. I'll leave it with that hint to an explanation, and would like to take you away that something like that exists. It is significant because we can calculate these eigenvectors directly using a NumPy function, and one of them, the so-called principal eigenvector, contains the same information that we got from the Markov chain. So if we can find the eigenvectors, we basically don't have to do any of the simulations. We can pull them out from our data directly. Yeah, so this short snippet of code is not doing any of the graph traveling simulation. It's basically taking the adjacency matrix and asking, what are the most important properties of this matrix? And one of the properties is that Lower Saxony is a very important location in this travel graph, and Berlin is not. Yeah. So and that is I hope this illustrates that there are more powerful tools to find in the field of linear algebra. Before I finish and ask whether there are more questions, I'd like to leave with a piece of hint, because here on the core web page that I made for this course, you find not only the notebooks and then a web version of all the exercises. I also put a couple of links here because you say maybe say, okay, all of this is interesting. I see that linear algebra is relevant. I now have a basic understanding how I can multiply vectors and matrices, and that I have to be careful with square matrices, and there are distances and a couple of other tools. And you have seen a couple of applications. Now, how to go on from here? If you say you want to gain deeper knowledge on this, I have a couple of recommendations. Yeah, I put here some links to some in-depth courses, but my two most important ones is the linear algebra videos by 3 Blue 1 Brown. This is, in my opinion, by far the best material that you can find to get an introduction that really thoroughly explains you concepts on linear algebra. I'm pretty sure that some of you have seen the 3 Blue 1 Brown channel already, because they've made videos on yes, the link source is freely available. I think I can put in the URL into the chat box. Thank you for asking. The videos are free as well. They cover tons of math topics. They have a separate channel for linear algebra that explains dot products and matrix multiplications and eigenvectors and determinants and all of that in detail with nice animations, very patiently. I think on linear algebra alone, there should be something like 6 hours of video material in that basically takes you off where this workshop is stopping. The other thing that you might want to do if you say, okay, I want to get going with linear algebra and actually do some stuff, but I need literacy in NumPy and do things with Python. I recommend the second link. This is my collection of graphic manipulation things using vectors and matrices. You saw a couple of examples of that, how you can use vectors and matrices to make diagrams and pictures. This graphics with NumPy, I don't want to call it a tutorial. It's more like a playground thing. It contains images like this, and each of them comes attached with a piece of NumPy code that produces the image and gives you some ideas what to try out next. Yeah, so because NumPy, of course, NumPy is primarily written for linear algebra, but there are many practical things that you will need when moving data around that you won't find in an algebra textbook. It's more like of a practical, it's more on the practical programming side. Good. Now, let me see what questions we have, because I do have times. This beautiful question. In which cases should you use NumPy instead of pandas? The pandas is great for making diagrams, for data analysis, for working with data that is not only numerical. Like pandas is really good with timestamps. If you have dates and times, pandas is the way to go. Yeah. If you have categorical data, if you have text fields, NumPy is simply not useful. If you reach a point, but pandas, what pandas does algorithmically is does not go very deep. Yeah, so I see pandas as an Excel-like tool for using Python code. It's incredibly useful, but mathematically, it doesn't go very deep. If I need something mathematically deeper, I may need to use other libraries, yeah, like that contain sophisticated algorithms, like scikit-learn for machine learning, or TensorFlow or PyTorch for neural networks, or SciPy for generic scientific algorithms and functions. And NumPy is the piece that is connecting all of these. Yeah, so if you do work with bigger amounts of numbers in Python and you want to do calculations with them, there is really no way around NumPy. Pandas is the thing that is built on top of NumPy to good. So I hope this this overview has been useful. So I see that we saw a couple of different things. The material is available. You have the notebooks. So wait, which link would you like me to share? So if you need the link for the presentation slides and notebooks, it's all on. I put the link in the chat box. It's all on Academis EU. I have a couple of other Python tutorials on the main page, apart from the NumPy and linear algebra material. Feel free to take a look. It's all free to take away. Good. I'm not seeing further questions. Oh, there's been, okay. Could you share your contact details on any follow-up question? I'll simply link to the main page, because you will find my my email there. I'll also put the email in the chat box. Feel free to contact me. So that is public information. Thank you for asking.
Thank you, Kirsten. I think there's seems to be no other questions, so I think we can start to close off the sessions. Thank you again very much to Kirsten for organizing very insightful workshops on the geometry of data, the linear algebra for data science. I hope everyone has learned something useful for this course, and you've had some inspirations on what you want to use the knowledge for. I think mathematics has been it's very challenging to learn, and I think you probably will have to maybe rewatch or review some of these slides later on. So like the way that I think I've always learned mathematics, and I think Kristen can also collaborate on this, which is you never really understand it the first time you look at it, and it's always the review process, and it's trying out problem sets and learning it over and over again that kind of gives you that aha eureka moments where you actually things connect together in your brain and you understand what all of these means actually. So
Thank you for that comment,
yeah,
Hui. I can totally second that. Um, Everything apart from vectors, I had to learn multiple times.
yeah,
Yeah. So and the math notation that you find on Wikipedia or on a course that is made for people who are studying, I don't know, mathematics, computer science, they go very deep into things, and it's not helpful for people like us who come from the practitioner sides and say, you like I have very often had this experience even when preparing this, that I go on a Wikipedia page. It lists me 2 pages of equations, and I say, damn it, all I want to know is what is this good for? This is hard to find out. It's not in this is not an easy part.
yeah. No, absolutely, I agree completely with you as well. And so don't be discouraged if you don't understand any part of this sessions. Review and look into things, and especially don't be discouraged if you don't understand things. And you have all these tools available, right? ChatGPT and all these AI tools can help you to explain things a little bit as well in case you do not understand things on a more high level view. And so yeah, please. I think the takeaway is. Don't be scared of math. It's very fun. It's very exciting. And also it's very useful for your work and for research as well. And for the next sessions, it will be on building AI agents, which will take place in exactly 1 hour at 2 p.m. Berlin time. So we hope that some of you will be able to join as well, but feel free to go out and grab some lunch, grab some dinner, and then come back when you can. Thank you again, Kristen. I hope you've also enjoyed teaching the course and looking at the questions and answering people's questions and had some experience about maybe what people expect in a math course online and how it works.
Thank you. It's been a pleasure to be around. Thanks for organizing.
Absolutely. So yeah, I will leave you to your vacation now, Christians,
Yeah.
and for everyone else, thank you for joining. And